Hello everyone. Today we are going to solve some problems on speed control of a DC series motors. Already in the previous presentation we have solved three problems, and this is the exercise problem which I have given in the previous presentation. In this presentation I will solve this problem. Now let us read out this problem. A DC series motor runs at 900 rotations per minute and takes a current of 25 amperes when connected to 220-volt DC supply mains. The total resistance of the motor is 0.5 ohms. Determine the value of resistance which when connected to in series with the motor will reduce the speed to 600 rotations per minute. The electromagnetic torque being then half of its previous value. Assume flux to be proportional to the field current. Now let us see the given data. Here the supply voltage is given as 220 volts, and the total resistance of the motor is 0.5 ohms, and the initial speed represented by N1 is given as 900 rotations per minute, and the initial current, that is IA1, is equal to 25 amperes. And here we have to determine the value of the resistance to be added when the speed gets reduced to 600 rpm. That is, N2 is given as 600 rpm. The initial electromagnetic torque T1 is equal to T, say, and after adding resistance, the torque, that is the electromagnetic torque, has reduced to T by 2. And also we know that the back EMF equation E is equal to V minus IAR. In this one, we write the initial back EMF as EB1 is equal to V minus IA1 or T. If we substitute the values in the above equation, we get 220 minus 25 into zero point 0.5. On solving this, we get the answer as 207.5 volts. This is nothing but this is the initial back EMF. EB1 is equal to 207.5 volts. And we also know that the back EMF equation EB is equal to 5ZNP by 60A. From that equation, we can write as EB is directly proportional to phi N, where phi is the flux per pole in Webers and N is the speed with which the motor rotates. So if we remove the proportional and we keep a proportional to constant, we get EB1 is equal to KB phi 1 and N1. These are the initial values of back EMF, flux and speed before adding the resistance. As the flux is directly proportional to the current, we can write the above equation as KB into IM1 into N1. Writing the proportionality constant is equal to, that is KB is equal to EB1 by IM1 N1. If we substitute the values, we get 207.5 by 25 into 900. On solving this, we get the value of KB as 0.009222, and we know that the torque T is directly proportional to phi Ia, where phi is the flux and Ia is the armature current. From this we can write T is equal to K1 into phi 1 into Ia. Since the flux phi is directly proportional to Ia, we can write I as phi 1 is equal to IA. So from that we get T2 by T1 is equal to KT into IA2 square by KT into IA1 square. We also know that T2 is equal to T by 2. On substituting these values in the above equation, we get T by 2T is equal to IA2 square by 25 square. Here KT gets cancelled. So from this TT also gets cancelled. On solving this, we get IA square is equal to 625 by 2, which is equal to 312.5. From that IA2 is equal to root of 312.5, which is equal to 17.678 amperes. Let R is the value of resistance connected in series with the motor for reduction of speed from 900 rotations per minute to 600 rotations per minute. Then if we substitute this in the back EMF equation, we get EB2 is equal to 220 minus 17.678 into zero point 0.5 plus R. From that we get in the previous equation EB2 is equal to 0.00922, that is the constant which we have already got here, and 17.678 is the value of IA2 and 600 is the value for speed, secondary speed. Means EB2 is equal to K into IA2 into N. This is from the back EMF equation. If we solve that, we get the back EMF value as 97.82 volts. If we substitute this 97.82 volts. In the above equation, we get 97.82 is equal to 220 minus 17.678 into zero point 0.5 minus 17.678 into R. On solving this, we get the value of R as 6.4 ohms. Means R value is 6.4 ohms. Since this is the resistance, when we connect this resistance, the speed gets decreased to 600 rotations per minute. Now let us see the next problem. A 250 volt DC series motor draws full load line current of 30 amperes at the rated speed of armature and series field as 1 ohm. The brush voltage drop is 3 volt. Find number 1 the speed of the motor when the load current drops to 20 amperes. 2 the speed on the on removal of load when the motor takes only 1 ampere from the supply. The third one is the internal horsepower developed in each of the above cases. Neglect the effect of armature reaction. Now let us solve this. Before solving, you have to study this problem thoroughly. And we have to find what is the given data and what we have to find. And it is given that the supply voltage V is equal to 200 volts and current IM1 is equal to 30 amperes. The current IM2 is equal to 20 amperes and also given that IM3 is 1 ampere. The initial speed N1 is given as 750 rpm, means rotations per minute. And the total resistance means the resistance of armature and series field winding RSC is equal to 1 ohm, and the brush voltage drop is given as 3 volts. We know that the back EMF equation EB is equal to V minus IA into RA plus RSC, and if we also consider the brush drop means it will be subtracted from the this value, means EB1 is equal to V minus IM1 into RA plus RSC minus VB. From the above given data, we know all the values. If we substitute those values, we get 250 minus 30 into 1 minus 3. In the given data, the supply voltage is given as 200. Sorry, it is 250 volts. Kindly change that. On solving this EB1, we get 217 volts. And to get EB2, you know the formula EB2 is equal to V minus IM2 into RA plus RSC minus 3 into 20 by 30. On substituting those values, we get 250 minus 20 into 1 minus 3 into 20 by 30. From that, we get 250 minus 20 minus 2, which is equal to 228. It is the value of EB2 is 228. From the equation, EB is equal to 5ZNP by 60A we can write as N2 by N1 is equal to EB2 by EB1 into phi 1 by phi 2. And we know that flux phi is directly proportional to the armature current IA. We can write the above equation as N2 by N is equal to EB2 by EB1 into IM1 by IM2. If we substitute all the values, we get N2 by 750 is equal to 228 into 30 by 217 into 20. We get 1.576. From that, N2 is equal to 1.576 into 750, which is equal to 1182 RPM, means rotations per minute. And the second question is, when current is 1 ampere, then speed N2 is equal to 1182 RPM. Then EB3 is equal to V minus IM3 into RA plus RSE, which is equal to 250 minus 1 into 1 is equal to 249 volts. Since current is very less, so much drop is neglected. From that, N3 by 750 is equal to 249 into 30 by 217 into 1. On solving this, we get N3 is equal to 750 into 34.424, that is 25,818 rotations per minute. And the initial horsepower is equal to EB into IA by 735.5. And substituting those values, we get 217 into 30 by 735.5. We get the answer as 8.851 HP. And the HP2, we'll get the HP2 as EB2 into IA2 by 735.5. That is 228 into 20 by 735.5. That is 6.2 HP. And HP3 is equal to 249 into this 249 is nothing but it is the EB3 value. EB3 into 1 by 735.5. We get the answer of HP3 as 0.3385 HP. Now let us solve the last problem. That is a 220 volt DC series motor runs at 500 rpm when takes a line current of 25 amperes. The resistance of armature is zero point 0.2 ohms and that of series field is zero point 0.6 ohms. At what speed will it run when developing the same torque when armature diverter of 10 ohms is used? Assume a straight line magnetization curve. Let us see the solution now. Here the given data is The supply voltage is given as V is equal to 220 volts, and here the armature resistance is 0.2 and the series field winding resistance is 0.6. So the total resistance RT is equal to 0.2 plus 0.6, which is equal to zero point 0.8 ohms, and the initial speed is given as N1 is equal to 500 rpm. The initial current IA1 is equal to 25 amperes. The armature diverted resistance R is equal to 10 ohms. Final speed at constant torque N2 is equal to how much? We know that the back EMF equation EB1 is equal to V minus IA1 into RA plus RSC. We have written this as the total resistance RT. We substitute all the given values in this. We get 200 minus 25 into zero point 0.2 plus zero point 0.6. On solving that, we get the value as 180 volts. Let the motor input current be I2 when armature diverter is used. And the series field winding voltage drop is 0.6 into I2. So the potential drop at brushes is equal to 200 minus 0.6 into I2. Therefore, armature diverter current is equal to 200 minus 0.6 I2 by 10 amperes. The armature current is equal to I2 into 200 minus 0.6 into I2 by 10. We get IA2 is equal to 10.6 I2 minus 200 by 10. As the torque is same, we know that the torque is directly proportional to phi Ia. Since the torque is same, we can write as phi 1 into Ia1 is equal to phi 2 into Ia2. From that, 25 into 25 is equal to I2 into 10.6 I2 minus 200 by 10. On further solving this, we get 6250 is equal to 10.6 I2 square minus 200 I2. This will be a quadratic equation. On solving this, we get the value of I2 is equal to 35.6 amperes. Now, if we substitute this in the potential drop at brushes, then we get 200 minus 35.6 into zero point 0.6. That is 178.6. And to find the IA2 value, we substitute this I2 value, we get 10.6 into 35.6 minus 200 by 10. We get IA2 as 17.74. And the EB2 value will be 178.6 minus 17.74 into 0.2, that is 175 volts. From the equation EB is equal to 5Z NP by 60A, we get N2 by N1 is equal to EB2 by EB1 into phi 1 by phi 2. Since the phi is directly proportional to current I, we can write as N2 by N1 is equal to EB2 by EB1 into I1 by I2. On substituting all the values, we get N2 by 500 is equal to 175 into 25 by 180 into 35.6. We get the secondary speed N2 is equal to 314 RPM. Thank you very much for listening.